Recording in progress. Okay, and now it's right. Good. Wow. Experimentalists.
You can be a good.
I can't. Proof by negation. All right, my watch says 10:45 and 11 seconds. Don't want to waste any precious seconds.
All right, well, good morning. Pleasure to that Otten. Member of the department. That is a variety of things, but quantum computing, today's focus primarily, and today we will tell us about quantum computing and applications thereof.
Great, yeah, happy to be here. Happy to see lots of hopefully excited faces. We've got a lot of time. I usually don't give 90-minute talks. I give 45-minute talks, which means that I expect interaction to help fill the time. If not, we're going to be standing here staring at each other. That'll be boring. Before we begin, though, I'm going to introduce myself, and then I'm going to ask a couple questions of you guys to sort of gauge what the audience is. So I'm Professor Otten. I've been here at Madison for about a year and a half or so. Before this, I was in industry. I was at HRL Laboratories, which is a research laboratory on the West Coast. They are kind of famous for inventing the laser. It's a cool thing. And I was doing quantum information science research like I am today. Before that, I was at Argonne National Lab down in Chicago. And I got my PhD from Cornell University. My research broadly focuses on theoretical and computational quantum information science. So what you guys are all here to learn about in these few days. I center my research around the qubit, which you've probably heard a lot about. We'll talk more about it here too. And I ask two very big questions. One is the topic of mostly today's work is if we had a lot of qubits, just as many as you wanted, and they were free and perfect and everything. They don't have to be perfect, but they were sort of unlimited. What would you do with it? What are the specific things that one would do if a black box, magic quantum computer, was dropped on your desk today? And you probably hear in the media and in popular science in various locations that quantum computers are going to change the world. We truly believe that, and we believe we're on the path there. We should start thinking about how that's going to happen. We might say something like, it's going to cure cancer, but there's a million ways to cure cancer. There's a million different cancers. It's really not precise to say that a quantum computer will cure cancer. But what my research tries to do, and what you'll hear about in this talk, is identify specific applications. I'm going to simulate this molecule, which I think is useful for this type of cancer, which I think will be useful in therapeutics for this disease. And then decide exactly how one would map that onto a quantum computer. Or even a classical computer or a neuromorphic computer. At that point, I just care about it as an interesting application. What atoms I'm going to use? What are the distances between those atoms? What is the chemical, how am I going to encode the electronic wave function? How am I going to embed that onto a quantum computer? What is the quantum algorithm I'm going to run? What is the error correcting code I'm going to use? And what is the hardware I'm going to use? There are a lot of decisions to be made on there, but until you've made every one of those decisions, you can't really say whether a quantum computer is going to be useful or not for a given application. And by the tools, though we don't have those unlimited number of qubits, we can still kind of fake it out and ask what would be the cost going through that chain of decisions we've made. And that allows us to identify whether there's better things that one could do. It turns out the Trotter time stepper is the really, really slow thing, so let's use a different one. So that's one half of my research. The other half is realizing that we don't have an unlimited number of qubits, that they're actually very, very, very expensive to build and very, very limited in quantity. And so I work very closely with my experimental colleagues, some of those you've heard from, including Robert McDermott earlier this week, Mark Saffin, you're going to hear later today, Mark Erickson, ones who are in the lab making these qubits. And I worked very hard to help them make their qubits better. I don't make qubits. Don't trust me to touch a real laser or a real experiment, but I know how to use regular computers really, really well. I can run on very large classical computers. I can do simulations. I can help with applied mathematics, machine learning, what are the problems that you have in, say, calibrating your machine? How can we bring to bear some of the great advances in classical computing, GPUs and machine learning, for instance, to really make that hard part of building a quantum computer easier? So together, thinking about what we can do with qubits and thinking how we can make qubits better, my lab tries to accelerate the path to useful utility scale quantum computing. All right, so that's me. Great. I just want to sort of brief survey of those in the crowd. How many of you are from UW-Madison? Okay. How many are from sort of one state, like within the state of Wisconsin, but not Madison? All right. And then going out farther, maybe one state away, Minnesota, Illinois, Iowa. And then any further than that? How far? That seems pretty far. All right, we like Maryland. Maryland's a nice place. I think there's a direct flight between Maryland and Madison, so that's good. Great. And then how many of you are freshmen? Sophomores? Juniors? Seniors? Graduate students? Okay, good, a good mix. And then how many of you say would respond favorably to, I know about quantum computing? Okay, all right. Very happy about that. Good. So before I even get into quantum computing, I want to think about part of my research has nothing to do with quantum computing. Like I said, it's identifying big challenges that can be solved with computers and then identifying whether those are useful for quantum computers. So I have a marker and a whiteboard. What are some big challenges that one might use a computer, quantum or otherwise, to solve? What do you think? You guys have all taken classes. You've probably taken science classes. What do you think a quantum computer or even a classical computer or machine learning or something, what do you think, a big challenge is that we could identify and potentially look at as a use case for a new computational device, such as a quantum computer? I'll write them on the board. Supply chain. Supply chain logistics. And I'm going to put next to that a class that I think that is an optimization problem, given, maybe that's what you meant, maybe not. Okay, good. And that's given a bunch of boxes and places to go and a limited number of trucks. How do we get all those boxes places? Good. All right. Can you think of a specific partial differential equation? All right. Fluid dynamics. And so that we're going to call a PDE. And so there you might think of several problems in fluid dynamics about solving, say, the flow over a hypersonic jet. And that because you're going so fast, classical solvers like Navier-Stokes just sort of fail and give bad answers. So we want really, really high accuracy. Very good. Front row. Drug discovery. Good. Okay, and drug discovery is interesting. It's sort of a quantum chemistry problem, but it's also, and as many of these turn out to be, it's a discovery problem. And so one can say, I have a device that's capable of solving for a specific drug and giving you the answer whether it's good or not, but then you still have to search over hundreds or thousands or billions of candidates. And so just because you have one really, really fast solver that'll tell you whether a drug's good or not, whatever that means, if you want to discover something, it's now a search problem over a really hard quantum mechanics problem. Okay, sorting through, well, I'm going to use the word analyzing maybe. Okay. Analyzing big scientific data. And this one is, it's a bit hard for me to classify because this could be like a machine learning and optimization. It also could be something like anomaly detection, right? Is there something that's off? So I'm going to put the vaguish ML there because that might be a good classifier. Anything else? The mini body problem, okay. So the mini body problem, generically, to give the context of that, we think of as a very physics, in a very physics way. There's lots, you're talking about the electronic mini body problem or sort of just classical three body problem? Yeah, sure. So generally, if there are lots of things interacting, it turns out it's really, really hard to solve for like it's very, very hard for us to like do it analytically. But even especially in quantum mechanics, if you have a lot of electrons interacting, just understanding those interactions becomes quite difficult because they grow sort of exponentially. It turns out drug discovery is sort of trying to solve the many body problem, but a very restricted set of that, or a set of atoms that might be biologically relevant. Factoring numbers, yeah, this is the prime, if you will, use case of quantum computers, factoring, I'll say prime numbers. And that has cryptography. We'll call it crypto. Implications for cryptography that today, when you get on your bank website and you go to check your how much money you have in your bank, hopefully it's a positive number, and your computer and their computer does a sort of handshake that is built upon large prime numbers. And the fact that this is secure rests upon and something that's not proven in complexity theory, but generally accepted, is that we don't have an efficient way to factor prime numbers. And then in the 90s, a guy named Peter Shor came along and said, you could do this with a quantum computer. And since then, we've sort of moved forward and forward. And just in the last week, there was a paper from a scientist named Craig Gidney at Google, which claimed that with newer advances, you only need about 1 million qubits to break RSA 2048, which is the current standard. So at one time, we thought it was maybe 100 million qubits, but now with realistic understandings of the noise and error correction and the various architectural details that are necessary for a quantum computer, Craig Gidney thinks you can get down to about 1 million qubits, which is an interesting number. It's small. It was 20 million qubits running for 8 hours a few years ago. Now it's 1 million qubits running for about a day. And that was not with computers to test on. It was just through thinking about algorithms. Yeah. Yes. Sure. Yeah. There's always, there's assumptions that he made in this paper, which if you read the paper, he'll explain, are maybe not the best assumptions, but are the assumptions that were made in previous papers. So he's trying to keep them level so we can show progress. But yes, if you can make a plot, and the plot is years and number of qubits, and if you plot how much it takes to factor prime numbers, it's going like this. If you plot how many qubits we have, it's going like this. And this interaction point is somewhere between maybe 2033 if you're optimistic and 2040 if you're a little pessimistic. That's assuming, that this isn't the final point in the algorithmic space, and this isn't the final point in the qubit space. So there's always going to be improvements. We're scientists, we're doing research. So, maybe 2033 to 2040 is reasonable. So that has implications. There's a slight, I will just add for context that just because you can do it once in one day doesn't mean you're going to necessarily be able to get all the nuclear codes, because you have to crack it 100 times or 1,000 times, right? There's so many messages going through the pipes of the internet that your ability to crack one version, like one single message, is good enough to do it in one day with 1 million qubits would be good enough to get you one document. And you sort of probably want to get 1 million documents. So, your 2033, probably your bank, maybe you're rich, I don't know, but your bank is probably safe. My bank is safe, but maybe Donald Trump's bank's not safe, because he might be a target. But by 2040, when you have way more qubits and way more quantum computers are online, then it starts to become more scary for a regular person. Security by obscurity is not a good way to go. So there are methods of post-quantum cryptography that have already been studied, are being adapted. I think some iPhones already have them in. So yeah, good. That's a good number of things. Is there anyone has a desire to add one more to the list? I'll just say a couple without adding them. So another one is carbon capture. There's a lot of carbon in the air. That's bad. Climate change. So one might want to develop a way, a new molecule or a new catalyst, we call it, to capture carbon. Turn it from, say, in the air, hanging out there, turn it into something solid, and then bury it. So putting it back into the ground. And there are ways to do that, but they're very inefficient. They actually produce more carbon than they take. And so one needs to optimize that process, and it becomes perhaps a quantum mechanical problem. Another one is, it turns out about 3% of the world's electricity goes into making nitrogen, something called nitrogen fixation for fertilization. A long time ago, we used to just get it from bat guano. There are these big piles of bird poop and bat poop that would just sort of like in the ocean, and navies would fight over these because that fertilizer is very, very valuable. Nowadays, there's something called the Haber-Bosch process that one can do at an industrial scale to make fertilizer, which then goes into growing food, such as corn here in the Midwest. We need that fertilizer, but it's very energy intensive. Turns out nature, there's a very specific molecule called nitrogenase that just does it sort of passively. And we don't know how to scale that up in an industrial setting to really make it useful. But because it exists in nature, that implies that there might be a way to engineer it. And so understanding specifically the iron molybdenum cofactor of nitrogenase is another really interesting problem. And what I'm going to talk about for the next 20 minutes is another one. It's not moving. Is corrosion. Corrosion is another very big problem. It costs the American economy about $125 billion. This was in sort of 2022 money, which is a lot less now. So $125 billion went into fixing things that corroded. Corrosion is rust. We here in the Midwest drive our cars in the winter. This gets a lot of salt and water in it. Eventually, you'll see rust showing up, and that rust can affect the structural integrity of your car. It can sort of look bad. Eventually, you have to fix it, or your car breaks down. That happens not just to individuals' cars, but it happens to all sectors of the kind of utilities. Water pipes corrode, batteries, electric lines, propane tanks. These things are big. Telecommunications, we have 5G. There's a 5G tower. That's going to rust, and somebody has to fix it, or it's going to fall over. So that's, 35 billion. Then there's infrastructure like gas pipes and things, airports, all those also rust. Cars, planes, trains, automobiles. The government has nuclear waste and sort of their own fleet of vehicles, which have to be cared for. Essentially, rust is this process that just always is happening, corrosion, and we have to fix it. Maintenance is a very important part of keeping things going, and a very important part of maintenance is dealing with corrosion. It also turns out that corrosion is a very difficult problem to understand. We see corrosion, we feel corrosion. I can touch it. My car corrodes. That is this here is a picture from a plane part, courtesy of Boeing, that had some corrosion in it. It's a hole. You can put your finger through it. However, it turns out that corrosion is the processes that control corrosion are caused by quantum mechanical effects at the atomic scale. So that is the big thing that you can touch, put your finger through. These are atoms, which are very small, and they're very, very hard to see. And their individual water molecules are constantly going in and out on top of and off of the surface, and they're essentially pulling the interactions between the water molecules, as we understand it, is pulling individual atoms off. And that happens a lot. It's constantly happening. And if it happens long enough, you eventually get something that you can see. So it turns out to be a very difficult problem to solve computationally using a computer, because large time and length scales are what you actually care about. You don't care about an individual atom, you care about when your tower is going to fall over. And that's happening because of atoms and electrons. And so this kind of vast, many orders of magnitude difference in cause and effect makes it really hard to study, and then we want to study it so we can try and mitigate it. So what that comes up with is a big problem. One of these, to add to this list, is it's a materials design problem. So we want to come up with a new material to prevent corrosion and somehow control it. And this could be you build your whole plane out of a new super material that we discover. More reasonably, it's going to be a coating. You're just going to paint something on. So it's something called a sacrificial coating. You paint it on once a year, it corrodes instead of the aluminum body of the plane. And then that sort of delays the structural damage and kind of controls it. And so magnesium-rich sacrificial coatings and magnesium alloys is actually a very specific way to deal with corrosion. Like I mentioned, when you say drug discovery, you have to be very, very specific if you want to cure cancer. If I want to come up with an algorithm running on a quantum computer that actually solves the problem, I have to be very specific in my problem statement, which on this side is magnesium-rich sacrificial coatings. We know that turns out that that's what's used today oftentimes is magnesium-rich sacrificial coatings, but they're not as efficient or effective as they could be. This is something called an aqueous corrosion problem. That means in water, aqueous aqua. And we kind of understand the basic equation, something called hydrogen evolution. I'll show that in the next slide in brief. So we understand the basic mechanism, but we don't have enough precision to do a design to say, let's try this is just magnesium. This is an alloy where you maybe put cobalt or something in there. Magnesium plus cobalt may or may not perform better than just magnesium. That's something that you would want to check. Right now, it's really expensive to check that. You have an experimentalist go and sort of mix vats of chemicals and hope that you understand what happened, then you paint it on, then you wait a year, so these things take a while to corrode, and you see whether or not it was better than the thing you did before. That R&D cycle is very, very expensive. We had a computational tool, a computational box maybe a quantum computer, which could just sort of screen out 100 candidates and say, go try this one. Nobody's going to trust my quantum computer to just start painting things on planes. They're still going to test it, but at least we don't have to test 100 things, and we might be able to test one. I will note, though, that the complexity of the problem is very great. It's not just aqueous corrosion. It turns out things corrode when it gets really hot as well. So high temperature corrosion, dry corrosion, jet engine, lots of fires coming out of that, that also causes the material to break down in a completely different way than the magnesium rich sacrificial coatings than aqueous corrosion. So you would have to do a completely different design problem to come up with a material that was more robust to high temperature. And so there you might look at niobium rich refractory alloys. So that's two of many, many types of corrosion. We're going to talk a lot about the magnesium-rich sacrificial coatings here today. By the way, ask questions along the way, of course. Good. So this is very chemistry. I'm not going to go into the depths of the chemistry here, but I will say that, we have a basic understanding through many years of corrosion scientists working on how aqueous corrosion works. There's 1, 2, 3, 4, 5, 6, 7 steps in what we call reaction coordinates. That means that along the way, things are happening, and they happen sort of in a usually well understood way. Most of the time, you have a hydrogen, so 2 waters kind of come in, 1 water embeds itself inside, then another water embeds itself inside. They're going to surround. 2 waters are going to surround 1 magnesium atom. It's going to pull that atom off, and then you've lost it. And that is, the 1 atom version of this that we understand. But what we really want to do is, use that basic understanding and put it into a design problem where we're not just looking at how it's happening one by one, which one can do with today's computers. We actually need to grow the size of the system so that we're studying these larger length scale properties. So we can see, what is this on a 100 atom scale or 1,000 atom scale, where effects like alloying, adding a new metal in there, can really reveal themselves to be either effective or not effective. Okay, and so when I think about solving a problem, I often think about it in steps. This is a cool, colorful graph that I've made that helps me understand what it means to help design a new anti-corrosive coating. So this can be repeated just to say that you could do this for every one of these different things. We could map out the steps one might take. And that's a really useful and an informative way of analyzing a new application. So if we wanted to ask, how could fluid dynamics be solved to help the world or make a lot of money or something, you could do something like this. I'm going to walk you through, without a laser pointer, I'm going to walk you through this specific instance. So we want to deal with corrosion, and specifically, we're going to look at magnesium-rich anti-corrosives. To do that, turns out we have to calculate that HER, hydrogen evolution reaction rate. That number, we believe, is informative about the actual corrosion rate one will see when you put it into an experiment. To do that, there's lots of steps, and this becomes sort of technical and algorithmic-y, so you don't have to understand every single node here, but one has to compute a reaction pathway, generate a model slab, and compute an activation energy. Then each of those are not defined in sort of units of math. So to compute a reaction pathway, you actually have to use something called a nudged elastic band algorithm. To do that, we eventually use density functional theory, which is which you'll hear about from Yuan if you haven't already. There's also, so that whole side is classical computing. We think those algorithms, those various nodes on this graph are relatively fast to do on a quantum computer. On a classical computer, that they have good accuracy and we don't really need to make them better. However, if you talk with corrosion scientists at Boeing who are really care about whether their planes are corroding, they tell us that computing this activation energy is really hard. They only know how to do it either approximately and then they get bad answers, or they can't run it for a big enough system and you get answers that are not informative of the real system that they want to do. So that's where we're going to invoke the magic of a quantum computer. I've not told you what a quantum computer is or why it's magical. That'll be the next part. But that is the part where working with an application scientist who really knows about it, we went through sort of analyzing various applications like this, and they said, if only we could have a magical black box which would solve that for us. That would make everything better. Everything else is easy, we understand it, but that thing, computing the activation energy, is hard. And so that's where quantum computing can come in. We've identified this solving a real world problem is rarely as easy as doing one thing. You've got to do 100 things. And quantum computers are, one kind of sucks today, but are not, when they're good, they're still going to be expensive and weird. And so we don't want to use that for everything. But for this one, computing the activation energy with an algorithm called quantum phase estimation turns out to be a good approach. That quantum algorithm has several components. It has a qubitized walk operator, a quantum Fourier transform. We have to do a state prep through, say, a matrix product state. Some of that also starts to become classical again. You might have to have inputs that go between quantum and classical. And this is just showing the richness of solving a problem. So I will talk about quantum computing in the next few slides, and I'll tell you a little bit about these algorithms. But this is how I like to do research from an application first perspective. I'm not thinking about the quantum computer. I'm thinking about what is it that we need to solve to change the world, and then breaking that down into parts. I can't say I'm not a corrosion scientist, so I don't know if this is the best way of doing it, but I work very closely with application scientists, like those who work in corrosion or drug discovery, to really understand what they think is the easy parts, what they think is the hard parts, what their current workflow is, and how we would supplement that with novel computational devices like a quantum computer. It's a good place to stand here for 30 seconds and ask for questions. Any questions? Yeah, it's a great question. So talking to a lot of people, networking is a version of this, but we tend to know from the quantum computing community what we think quantum computers will be good at. We think they'll be good at quantum chemistry. They may or may not be good at optimization. We don't have a good proof. We think they're going to be good at physics, and we think they're going to be good at cryptography. Machine learning is something where it's left in the air, because machine learning generally it just is results driven, not sort of theory driven. And so, when I worked in industry, I worked at HRL. HRL turns out to be co-owned by Boeing and GM. Essentially, I sort of sent a call out. Hey, does anyone have any hard chemistry problems? And eventually that got me connected to the corrosion scientists. Similarly, you could think of battery science. Batteries are something that's say GM, a car manufacturer, is very interested in. That's another place where, we have the intuition, batteries will be good. So I'm going to go to friendly people who know battery science, and that could be in an academic setting or it could be in an industrial setting, and really ask them questions. And it turns out sometimes it's really hard to get the right person who knows both the end goal of building a battery and the language of computation algorithms that I like to use. But In short, it's sort of talking a lot. You have your hand up too, maybe? Okay. Good. Then I will go on. Now we're finally going to talk about quantum computers. I think you've probably seen a qubit 100 times. You're going to see it 100 more times. Everyone likes to show you a qubit at a quantum science summer school. This is a nice visualization of a qubit. We call it the block sphere. A regular bit, classical, can be up 0, down 1, and that's where we sort of stop. You can put a lot of them together and get you get a lot of bit strings, and we build classical computers out of that and do classical logic. A quantum bit or qubit actually can sort of point up and down, but it also has projections along x, so out of the board and into the board, and y to the left and right. So it can, a sort of, a good quantum state can be anywhere of a single qubit, can be anywhere on the surface of this sphere. That's not enough to sort of prove that one can do corrosion modeling with a qubit, but it's sort of a great intuition to start. That's like the key building block. How does one build a qubit? Well, I'm not an experimentalist, so I'm not the best to talk about it, but I will say that there are people in this building and who are talking to you who will tell you more about it. I'll just mention there are many different quantum architectures. Superconducting qubit, CoLab, I think they were one of your earlier speakers. They make very pretty pictures like this. They run at very, very low temperatures in dilution refrigerators. Neutral atoms, they trap these little dots there, individual single atoms. It's wild to me that one can just hold a single atom. Mark Safin will tell you a lot more about that later. There are semiconductor and quantum dot qubits. Mark Erickson, I think, is talking, and he'll tell you about those. That's where we actually trap a single electron in a silicon device. And so we make something called a quantum well. One electron falls in, and then we have a nice way to control that. It's also built upon silicon technology, and that's really nice because one of the things we're really, really good at is making silicon things, because we need to make billions and billions of transistors every day to feed our cell phones and now AI computers and all these things. There are other ones like photons, single particle of light, trapped ions, etc. They've all demonstrated limited use in quantum computing applications. I might need to start stripping away the word limited as time goes, because we're getting more and more expansive in the uses of these various devices. But there's also novel qubits being developed, and they could have interesting advantages. Microsoft talks about a topological qubit, a Majorana mode, which is relatively contentious in the scientific community, but they're pushing ahead, and there's lots of media about it. One could imagine having a molecule or a chain of molecules to do qubit stuff. There's lots of novel systems, but I think superconductors, neutral atoms, semiconductors, photons, trapped ions, that sort of first list is the one which has the most kind of industry investment, the most startups, the most well-developed technology. I, though, am not an experimentalist, so all of that looks the same to me. It all looks like what I like to call an open quantum system. I'm a theorist. I get to put at least one equation on my slides, even if nobody else understands it, because that's my prerogative. This is one of my favorite equations called the Lindblad master equation. It's sort of a generalization of the more famous Schrodinger equation. Rho is something like the wave function psi. It describes a classical mixture of wave functions. And then we have H, the Hamiltonian. That's the kind of natural physics that's happening. H of t is maybe a time-dependent thing, a laser pulse that you're going to use to control, or a microwave pulse. And then this L is a so-called Lindblad term, which describes the decoherence, that is, noise effects that we don't like. And so math, and then picture, this picture looks like 5 qubits sort of hanging out, pointing in various ways. I've drawn these little lines that show coupling between them. They can talk to each other. This is a laser pulse coming in, which might allow us to flip a qubit and control it and do some interesting work like a quantum algorithm. And then you've got perhaps information just flowing off into the ether and we don't want that to happen. That just sort of is an effect which is unavoidable and is an important part of understanding quantum computers and qubits. And so because noise is like a key part of the physical qubit, it's important to, I think, tell you a little bit about two main error channels that most of these qubits feel. One is known as amplitude decay, sometimes called T1. If you go to IBM Quantum Experience and click about their quantum computer, they'll say our T1 times are 100 microseconds. What is T1? Well, it is something that represents amplitude decay. If you start your qubit in the one state and you're saying, all right, we're good to go. I'm just going to leave it there. I'm going to walk away. I'm going to come back in an hour. Well, sometimes it just goes to 0. And you didn't want that to happen. You just wanted it to sit there. That is called amplitude decay. And it happens kind of randomly. This is quantum mechanics. Things are often random, but predictable. If you just looked at, say, time, and you can think of as microseconds is the best unit. Sometimes in trial 1, we only lasted 0.1 microsecond. In trial 4, we barely had any lifetime, but in trial 2, we lasted over 2 microseconds. That, if you just repeat the experiment over and over and over, randomly you're going to have this ejection of say, a photon that flies off into space, and you'll never get that information back. You can do that a million times. You can take an average, and you can see that it actually is well explained by an exponential decay. As these things are wont to do, you have a mean. Lots of times it happens early. Sometimes you actually get pretty long, but we tend to think of the point where it goes to about 1 over E, Euler's number, as the sort of T1 time. Another way to look at this is looking at the average evolution of a block vector. So we started in this time, instead of starting on 1, I started sort of on the hemisphere, and I want it to stay there forever. I don't want it to decay, but nature is fickle and doesn't allow me to do that. And now it's going to decay, and we can see that the sort of exponential decay is very fast at the beginning and slow at the end. So that's amplitude decay, one of the bad errors we don't like. A second is dephasing. This one, yes. Yes. No, it is, if you're imagining you have a single atom and you excited it with some energy and it's just sitting there, eventually it's going to fall down and it's going to release a single photon of the energy of that. I can draw this. So you have 0, 1, and this might be something like, I don't know, 3 eV, which is some unit that might be optical, and experimentalists can tell me whether 3 eV is optical. I don't know. So this is 1, this is 0. You put your quantum in the one state. We like to draw them like ladders here. And then at some time in a discontinuous quantum jump, it goes down to 0 and radiates off a photon of 3 eV. And so one can just sort of, maybe you've heard of Geiger counters or sort of seen a nuclear decay. You sort of hold it there and it's click, 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 click. That's very similar to what's happening here, that things are decaying kind of randomly and in a discontinuous way. Amplitude decay is a sort of classical-ish error. One goes from 1 to 0. You can imagine in a classical bit, 1 flips to 0 sometimes. It doesn't happen that often, it turns out. Error rates on classical computers are like 10 to the minus 10. It's totally amazing. But quantum computers can flip 1 to 0, but they can also have a problem where you lose phase information. Instead of flipping from 1 to 0, you thought you were initially pointing on the x-axis, and something kicks you so that you're no longer pointing there. If you measured, you'd still be on about half. You haven't lost any energy, but you've lost now phase. And so what this looks like, very interestingly, is you just fall into the middle of the block sphere, because you no longer know which way you're pointing. Sometimes you point left, sometimes you're kicked to the left, sometimes you're kicked to the right. When you take an average of all these directions, you have no idea which way you're facing. And so you lose all so-called phase information. You still know that you're 50% 0 and 50% 1. You're a superposition of those two things, but you've totally lost any idea of which way you're pointing on the hemisphere. So you've so-called dephased. And so this is a more quantum error than amplitude damping or bit flip errors. Good. And so if one wants to go from a single qubit to a quantum computer, we cannot just draw bubbles all the time. It turns out that that's kind of a hard way to represent quantum information. So we use a totally new form. We use the block sphere to give us intuition about a single qubit. Now we're going to go to multiple qubits, and now we're going to use a different graphical language. This is a quantum circuit. We have here a qubit represented by a line. The line is sort of the life of the qubit. Sort of starts on the left, ends on the right, and things might happen to it along its path. This qubit starts in the 0 state and nothing happens. Maybe you could say there was some background noise happening, but we didn't try to control it in any way. So that is the basic idea. One can then start doing stuff to the qubit, and we usually represent that by a box with a letter in it. This is a Hadamard gate, an H gate. The Hadamard gate is quite interesting because it takes you from 0 to a superposition of 0 and 1. We like that, it feels quantum. That's one of the reasons why we start with the Hadamard gate. So a single qubit gate. At the end of this circuit, 0 start, Hadamard applied to it. You could represent the Hadamard as a matrix if you want, but we're just going to focus with this graphical representation. You end up with a state 0 plus 1 over square root of 2. We did that superposition. And so that gives us sort of the state on the block sphere that might be pointing along the hemisphere. However, one qubit turns out to be kind of boring for computation, and it's sort of really interesting for doing experiments, be interesting for doing sensing, which I'm not going to talk about. But when we talk about quantum computing, we often, as you'll see later, we're going to need 1 million of these qubits. So we want to build up something more complicated. Here, now we have 2 qubits, 2 lines, 2 lifetimes. We do a single qubit gate on the first, and now we have a new glyph. That's a C0 gate. The C0 gate flips the state of the target qubit. That's a plus. So do a modular addition on based on the state of the first qubit, which might be, if it's 0, do nothing. If it's 1, flip the state. As we saw in the previous slide, that Hadamard gate puts us in the 0 plus 1 state. So now when you get to this point in the circuit, you're in a cool superposition state. You don't actually flip the qubit or not flip the qubit every time. It's going to happen in an entangled way. This is how one generates an entangled state. Because that first state was superposed between 0 and 1, when we did that C0, it's if that first qubit was 0, we're not going to do anything. If that first qubit was 1, we're going to flip that second qubit. There's kind of 2 paths that the data could have taken, and that gives us, because we don't know whether the qubit was in state 0 and 1, we get this cool entangled state. And so now entanglement shows up. If one were to measure either of the qubits, measure qubit 0, the first line, and get 0, you know the second qubit was in state 0. That 0 there is always with that 0 there. If that first qubit, that first line was in the 1, the second qubit is also going to be in 1. That's sort of entanglement shown in this quantum circuit language. Good. So one can continually do this and add more and more and more qubits. And the number of digits I have to write down starts to grow. I could just do 100 qubits and then have 100 zeros plus 100 ones. That's a really cool state known as a GHZ state, which is cool and entangled. But if you sort of do a simple counting argument, the number of bit strings that one can do when you have 2 qubits could have been 0, 0, 0, 1, 1, 0, 1, 1. You have 3 qubits, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, et cetera, et cetera, et cetera. If you asked me to do that for 50 qubits, we would be here until I died of, I guess, dehydration, because I would have to list so many numbers and I would be very thirsty. So this is what is known as exponential scaling, and is one of the reasons that quantum computers can be very powerful, is because each additional qubit doubles the number of available states. This is known as exponential scaling. 2 times 2 times 2 times 2 is 2 to the n. Great. And this is one of the reasons why quantum mechanics is hard to simulate and why quantum computers may provide advantage, is that if we can utilize this large space in an interesting way, using the superposition and not just the number of states, one can get quite far. And so if you look here, this is just a plot, simple plot of exponential scaling, some linear thing, straight, it's a line, we like lines. You might have something cubic that sort of grows faster, and exponential grows as sort of one of the fastest ways to grow. And very quickly, something that would say take exponential time to simulate becomes totally unwieldy. Interestingly, the exponential thing is actually really, really easy at small numbers. And so depending where you are on the exponential scale curve, an exponentially scaling algorithm could actually be nice. You'd be good. Oh, right. If I'm at 3, I'm going to be better than the linear scaling algorithm. But if you go to 10, you sort of fall out. If you go to 100, it's the age of the universe. And I just want to point out an interesting thing, that if I had 100 classical bits, there would still be a 2 to the 100. There's an exponential number of bit strings. But we don't know how to use those exponential number of bit strings in a consistent way to really express that. On a quantum computer, those exponential number of quantum bit strings can be made in superposition states, which should give you the intuition that it has power that a classical system might not have. Good. Stop for questions. All right. So now we're going to go back. We with corrosion. We talked about quantum computers for a little while. Now we're going to go back and talk about how we're going to simulate corrosion eventually with quantum computers. So there's this big thing here, magnesium, cobalt, a bunch of waters, lots of atoms in there. There's not that many, I can count them, but this is a many-body problem. They all interact with each other. They all have a bunch of electrons. It becomes very, very, very difficult to solve. There are exact methods for solving this. What does solving this mean? It means, say, get the energy. This snapshot has some energy. What is the energy of this snapshot? It might move a little bit. What's the energy of that snapshot? You want to get the energy of this. That's what we mean by solve. An exact method, there's one called full configuration interaction. That will give you the answer. We know that will give you the answer, but it scales exponentially 2 to the n. So if you had, say, there's 1,000 atoms here. Each of them has a bunch of electrons. Typically, we look at electrons. That's what's really interesting. Only 300 electrons. There's way more than 300 here. But only 300 electrons would take memory equal to the number of atoms in the universe to store every possible configuration. So full configuration interaction is an easy to write down algorithm that is totally not scalable and is sort of the bad way to go. approximate methods, I mean, people have been studying this for 75 years since quantum mechanics, or 100 years, I guess, now, since quantum mechanics has been sort of invented or discovered. People have been trying to solve this problem and realize that full configuration interaction is not a good way to do it. And so there are a lot of really great, powerful approximate methods that exist on classical computers. A couple clusters from the quantum chemistry community. Density functional theory, also known as DFT, comes from more like the physics and material science community. They are really great because they scale polynomially. So you can say DFT, simulate this. It'll be kind of a hard, this one is an especially hard system, but DFT could give you an answer in a reasonable amount of time that's not, the age of the universe. But it has approximations. Those can be uncontrolled, which means we don't really know what they do. And it turns out they are, in practice, poor, especially for so-called strongly correlated materials. So in a system where lots of stuff is happening and electrons are moving around and there's exchange of electrons between the system and that system and it's trying to pull an atom off, there's so much happening that something like DFT doesn't really capture all of that physics and chemistry. And therefore, we need something better. And it turns out an algorithm that I briefly foreshadowed a long time ago, quantum phase estimation, works on a quantum computer, and we can prove that it works in polynomial time, order into the fourth. And so we don't know how to write a version of quantum phase estimation on a classical computer, which doesn't scale exponentially. But on a quantum computer, we have an algorithm, we have a solution. What is quantum phase estimation? Well, it's super complicated. And this is the part where I show complicated circuits that I don't necessarily want to explain in complete depth, but I like to show up. It's a quantum algorithm. Quantum algorithms, I mean, classical algorithms, if you take a sort of advanced CS class, classical algorithms start to get a bit hairy and maybe hard to understand. Quantum algorithms, similarly so, if not worse. This is a specific version of quantum phase estimation, which is really fast and admittedly really hard to understand. It's called qubitized quantum phase estimation. You start with some wave function psi. You do a bunch of stuff. There's the W walk operator, which has these awkward things called prep, select, inverse prep, and there's some rotations. What is the walk operator? Well, it turns out it's something like e to the I arc cosine. Wow, who uses the arc cosine? Well, we do here. E to the I arc cosine of the energy you want to get divided by some lambda, which is like the one norm of your Hamiltonian, times the y gauge. Great, I can say all those words. You don't have to understand them, but just sort of trying to convince you that we didn't make this up. There's some really cool applied math behind this. This arc cosine, why is that a choice? Well, it turns out that's like the most efficient way to do time stepping. Even on a classical computer, there's something called the Chebyshev method, where you time step by arc cosines. And you have to do this W, and then you have to do it a bunch of times, and you have to do 2m minus 1. And you see we're controlling this. There's a line. This is sort of generalized control gate. It goes on to a bunch of ancilla. We do a quantum Fourier transform. We get the answer at the end. And we read that off, and that gives us an answer. To try and give you a little bit of intuition for how this works, I will draw something. And so what you're actually doing here in very complicated quantum algorithm Z language is you're starting with some initial state psi. And we assume that that is the wave function, it's the ground state. We know it. That's the thing we want to calculate the energy of. And so this thing has a wave function psi. We want to know what the energy of that wave function is. We start in psi. We then do this walk, which essentially is doing some evolution like this. If you plotted what was happening in some complex idealized space, you would see something wiggly. okay? That wiggly thing is mapped onto a bunch of ancillas, and we do a quantum Fourier transform. What's a quantum Fourier transform? Not important. What's a Fourier transform? A Fourier transform takes you from a space where things are wiggly to a space where wiggly things are peaked. So this wiggly thing has a frequency that goes up and down. In frequency space, once you've done a Fourier transform, this is just math, it's not quantum math, it's just math, you get some frequency omega. And so what the intuition between quantum phase estimation is you're doing some weird walk and it's wiggling. And then you do a Fourier transform. It's quantum, but it is still just a Fourier transform. It's the same thing as a fast Fourier transform, just a different implementation. And you get at the end omega. And what that omega is through some complex mapping is actually the energy of the state. And so you do this time evolution on the quantum computer, a quantum Fourier transform, and you get out the energy of the state. And that's really great because I told you I needed to compute the activation energy. That was the thing I needed to do. And this is a quantum algorithm which gives you that activation, gives you the energy of that state. All right, great. I love questions. We'll start with one in the back. Yeah. It is qubitization, which is some algorithm primitive that we use. Yeah, so it's interesting. Qubitization is super inefficient at the small scale. If you wanted to do 2 or 3 qubit qubitization, you end up a 2 or 3 states. If your wave function psi, let's say you have 1 atom and you have 3 orbitals. Okay, I'm not going to draw anything. I'm just going to say words. A very small system, qubitization uses a bunch of scratch space. And so it's a terrible, terrible algorithm for small systems. So if you have, say, a size 1, you're actually going to use 100 qubits. If you use an alternate algorithm, which I didn't explain here, but I'll name drop, trotterization, great way to do time stepping, you use that size 1 would only use 1 qubit. What qubitization gives you is you have to take way less steps. Trotter, you might have to take 1,000 steps on size 1. So that would be a space-time volume of 1,000. 1 times 1,000 equals 1,000. But for the qubitization, you need 100 qubits and only have to do 2 steps. And so 100 qubits, only 2 steps, your gate depth is much smaller. So you have a space-time volume of 200. So it turns out to be better in the limit of this infinite qubit world. Omar? Yes. It's not exponentially deep. What you're essentially doing is each of those wires on top, each of these ancillas is 1 bit of information. And so if you want 8 bits of precision or 16 bits of precision, you exponentiate at different frequencies, essentially. So omega, W2 to the m-1 is like giving you the m-1th digit. And so it turns out it's actually quite efficient because you can get exponentially more exact precision by just adding 1 qubit at a time. And so one might use, say, 10 ancillas in practice for reasonable accuracy. Yes. I can press it. Yeah. Yes. Yep. And that's a very good observation. The difference is that we don't know how to sort of use all those bits at the same time. That's kind of the intuition you should think of. In a quantum computer, it is not that hard to create a superposition of all of those bits. It's sort of hard to think very clearly about how one uses that superposition in an interesting and useful way. But a really good working intuition is Classical bits, I just have to enumerate them if I want to use them all. Quantum bits, I can create a superposition of them. Good. All right, qubitization, it's hard. But because it is specific and precise, one can go and do a resource estimate. I can say, I'm going to use qubitization to solve a specific system of atoms that is useful for corrosion. So I showed you that big graph of how one solves it. One of those was generate a model slab. That model slab then comes into the solver, and it tells you the size of it. And then one can compile a circuit because we know what the circuit is. It's well-defined and specific. We can then compile that circuit and count how many gates were necessary to do that. And a very important gate to count is something called a T-gate. The T-gate is the hardest gate to do. The other gates are kind of easy. A T-gate is hard. So I'm not counting C-naught gates because C-naught gates are sort of easy compared to T-gates. T-gates are hard. I can also count the number of logical qubits that would be required, put that all together, and then I can give you a number, okay? What is the number? So let's look at a really interesting one that we really want to solve is red diamond, magnesium 17, aluminum 12, a second phase supercell. Great material science words. However, that would require 10 over 10 to the 18th T-gates on 400,000 logical qubits. That's a lot. 10 to the 18th is a lot. 10 to the 18th of anything is a lot. I mean, you should go, oh. We want something a lot smaller than that. So this analysis of this specific application actually led to a conclusion that we need better algorithms. That all of the choices that we made along the way, they were the standard natural choices that one would make. We're going to use this algorithm. We're going to use qubitization. We're going to use this factorization. We're going to use this. All of those standard choices that are in the literature turn out to be quite bad for this application. The thing that the corrosion scientist wanted to solve is going to take a lot of T-gates. Now, I'll contextualize what a lot of T-gates is in a minute. But before that, what is the scale of quantum computing? So a paper from 2023, it's now 2025, so I should update this slide, but it hasn't actually gotten that much different. Tried to do something useful. They said, evidence for the utility of quantum computing before fault tolerance. Fault tolerance means we have to use error correction. This was an IBM paper. They used 127 qubits capable of doing 3,000 gates. Okay, 3,000, 3 to the 3, 10 to the 18, 15 orders of magnitude. That's a really, really different scale. There's also the scale of 100 qubits, hundreds of thousands of qubits. So this is almost a negative result. It says corrosion with this set of choices we made is a bad choice. One can make better choices or come up with new algorithms. Maybe there's a set of things that you could do that makes this more efficient. This was done in second quantized spaces. What if we use the first quantized spaces? We've updated since then and find more reasonable numbers in the first quantized spaces. That's kind of the power of using tools from resource estimation and by thinking of an application first perspective. I didn't say this is the thing I can do with a quantum computer. What can I solve? There's use in that. There's utility in that. I said, what is the most valuable thing I can think of and also have a friend who will tell me how to solve it? We came up with this and we got some very, very large logical resources. But that's not the end of it. One actually has to take those logical qubits and turn them into physical qubits. And as I said, there was error along the way. You could have a whole lecture about error correction, and I'm happy to do some whiteboarding. But you can add on to the story not just logical qubits and logical number of T-gates, but you can then do a resource estimate of the physical runtime. And the physical number of qubits. And so that's what we did here. This is a different application. It's actually, that's a bunch of little oxygens, 12 oxygens inside of a buckyball. So a Buckminster fullerene, a relatively large one, C180. That's a bunch of carbon atoms. Why do we care about this? Well, it turns out that oxygen, O3, ozone, generally is in a bent state, and it sits in the atmosphere, and it's sort of bent. We call it bent ozone. And this is like not 120 degrees. I don't know. It's 137. Don't quote me on that. 137.5 degrees. That ozone we use to make rocket fuel. And we send rockets into space. And it's really great because we can send rockets into space. But there exists a version of ozone, which is actually a perfect triangle, which 120 degrees, we call it cyclic ozone. One would imagine that nature likes things to be perfect triangles, and I would have too, but that's not how ozone exists in the atmosphere. But we generally think from quantum chemistry calculations that this is stable if you can get there. But it's just really hard to get there. We don't know how to make it, but once you make it, it is sort of a metastable state. And it actually has way more energy than bent ozone. So if we made rocket fuel out of cyclic ozone, we could send, for the same cost, same amount, like number of moles of ozone, we could send more rockets into the stars, and that would be cheaper, and that would save less. That would be cool. But we don't know how to make it. And so one proposal how to make it is you put it in a Buckminster fullerene, you put it in a buckyball, you shoot some lasers at it, and the local environment caused by the buckyball actually makes it more favorable and stable to be in this state than that state. And so this could be an industrial process for generating it. Okay, that's that little nice graphic there. This one we found is actually a more, maybe it's not as valuable as corrosion. I don't think we don't send billions of dollars, $120 billion a year worth of ozone into space, but it still has some value. We found here that you can look at some degree of accuracy orbitals. We might need about 125 to get there. That only has a logical T count of 10 to the 13th. It's 5 orders of magnitude better than corrosion, so that's nice. What does that mean in runtime? If we assume that you do error correction, we can use the tools of resource estimation to tell us that's like 10 to the 8th seconds. 10 to the 8th seconds, that's a lot. That's too many. Really, we want to be in this sort of shaded green region. Like you'd love to be in 1 second, but I can accept 1 million seconds. That's not, it turns out not to be too long. But we need about a factor of 256 times improvement to go from where we are at our current resource estimates of 4 million qubits running for 10 to the 8th seconds to get down to a more reasonable runtime, so that you could imagine actually trying to design a buckyball that would allow you to create this ozone. You can make similar arguments about corrosion, drug discovery, all of these. They actually have to be relatively fast because solving one is not good enough. We also have to solve a lot. And so this is means we need improvements across the stack, as they say, the stack. I might be able to come up with a better algorithm because I like quantum algorithms, but I'm not going to be able to come up with a better qubit. But maybe Mark Saffman, who we'll talk to you soon, could come up with a better qubit than the one I put in my resource estimator. There could be a better quantum error correction scheme than say, the surface code that I assumed here. There could be a more compact chemical description. Even before we start thinking about quantum algorithms, are we thinking about the best, most compact way to represent the chemistry we care about? And if you just sort of get factors of 2 across the stack, we get a 2 in compact chemical descriptions, we get a 2 in quantum algorithms, we get a 2 in quantum error correction, we get a 2 in better performing hardware, you start to see exponential scaling in savings. These devices are so new, and so the technology is so young that it's very unlikely that we know the best parts of each one of these. There's lots of research to be done to optimize it. And in my personal belief is that you can get 2s everywhere. You might be able to get 5s everywhere. Craig Gidney was able to get sort of a factor of 20 over a couple years in the estimates of RSA factoring. You can do the same in chemistry. And so, that's where we sit now, is that we need to make everything better. But there's a lot of people working on it. Hopefully you all will be working on it someday and take your ideas and help us get factors of 2, because it really is going to be an effort across computer science, chemistry, materials, physics, to get us to, and mathematics, fundamental mathematics, to get us to the point where these devices are both big enough, but also the algorithms and the applications are compact enough. I think that's where I will end and stop for some questions. Yeah, the short answer is no. The long answer is kind of, but also no. So why do we talk about T-gates? It turns out there's a theorem that says that and it comes from group theory. Group theory is cool math. That you can simulate if you do everything, if you do something called the Clifford group. The Clifford group, that's polygates, XYZ, Hadamard's, that's a C-naught gate. All of those things can be simulated very, very fast on a classical computer. We know how to do that. I can do a 1,000-qubit simulation if it's just Clifford gates, if it's just from the Clifford group, and that's from group theory. Once you add one T-gate, okay, so that's Clifford group, but that's not universal. That doesn't allow you to do arbitrary quantum computations. The way I like to think of it, which is imprecise but useful, is that on our block sphere, a Clifford circuit just takes you to the node, the kind of poles. You can go Z minus Z, X minus X, Y minus Y, and you can go to all of those points, but you can't go in between them. So it's sort of kind of almost classical if you think about it. A classical is up, down. Clifford is up, down, left, right, back, forward. So it's a little more maybe a little more powerful than classical, but it's not fully quantum. When you throw in a T-gate, just a single T-gate, you sort of fall off those points, and it becomes hard to simulate. The more T-gates you have, the harder it is to simulate. A Clifford plus T is a universal gate set. So if you give yourself unlimited numbers of T's, you can go to any point on the block sphere, and that gives you universal quantum computation. And so one essentially designs the microarchitecture of a quantum computer based on the fact that Cliffords are easy and T's are hard. That's like the whole design of how these things. You have very special places called magic state factories, which are generating T states, which can be distilled down to T gates. Those T gates are injected into a circuit that did a bunch of Clifford stuff really easily, and then was like, I need a T gate. And then it waits for one of these factories to give you a T gate. There are people who think about, like, what if we just don't use T gates? You could rotate your code, and T gates could be easy, but X gates could be hard. And so one could imagine doing code rotations between a Clifford group and a different group, and group doing kind of rotations between two different groups, but that cost of rotation turns out to be more expensive than T gates. And one can say, what if I just do the T gates physically instead of having to do them logically? And then it turns out your success probability goes to 0 and you pay an overhead in shots. And so our best understanding today is you have to do something like a T gate. You could, maybe it's an S gate or some other named gate, but there's always going to be one hard thing. And so we count that hard thing. Good. More questions? Yes. Yeah, so magic state cultivation makes T states So to give some context, Gidney's a smart guy, he does a lot of stuff. One of the things that he's worked on is how to generate these T states through magic state factories. For a while, we used something we call magic state distillation, 15 to 1 or 20 to 4. They have these cool names. But a paper from Google, including Gidney, came out recently called magic state cultivation, where instead of trying to take a bunch of noisy things and make it into one clean thing, they took one noisy thing and tried to clean it up by repeating it lots of times. So they call it magic state cultivation. It's a couple orders of magnitude better than magic state distillation, the old way to do it. So that sort of takes the cost of doing a T-gate from being maybe 1,000 times more expensive than anything else in your system to being about 1 to 10 times more expensive than a C-NOT gate. So that helps reduce the total resources. And one of the reasons that we had, this was 20 million qubits for RSA. This is 1 million qubits for RSA. One of the improvements here was this magic state cultivation. Yeah, so what that changes is this axis stays the same. This runtime will change by a factor of, say, 5, because even though the T-gates are the most expensive, it wasn't 100% of the time, right? It wasn't just only T-states. So you'll get, you made T-states a factor of 10 faster, and that'll get maybe a factor of 2 or 3 in your runtime. Yeah, so when I plot logical qubits here, I assume that they have infinite lifetimes. So they are just totally live forever, which would mean infinite error correction. And then when I want to do physical resource estimates, I take the number of T-gates, essentially how many things I have to do, how long does it have to live, and then I calculate what is the amount of error correction I have to do to achieve that. And so, in this case of the red diamond, I would need about 10 to the minus 18th error rate for that to be a good logical qubit that I could use for my computation. Yeah. Okay. So this paper, they used only noisy qubits, not logical qubits, and they tried to do something they thought was hard. And they kind of did all of the things they could to make it as good as possible. I think there's a lot of tricks in here one can take about error mitigation and sort of mapping and compiling that are useful even going forward to fault-tolerant quantum computing. However, it's sort of, as these things go, one comes up with a problem. Haha, no one's ever solved this. I tried a quantum computer on it. And then 2 weeks later, someone's like, oh, I can solve that in an hour on my laptop. I just didn't try because it wasn't interesting. And so that's one of the issues of starting with, quantum computer first. What can I do with it? Is oftentimes you bake up fake, not necessarily fake, but you bake up problems which no one's tried to solve. And you say, I solved a new problem. And it's just because no one tried to solve it. No one who is sort of very good at, say, MPS tensor network methods tried it. So then this paper specifically was very quickly responded to by someone by Miles Studemeyer at the Center for Computational Quantum Physics, the Flatiron Institute. Does that answer your question? Sure. Yeah, it's interesting. So they do some simulation, they get result A. They can't necessarily trust their result perfectly because there's noise in the quantum computer, but they claim this is what we got. We got 0.3, that's our answer. Then another person comes using a classical computer. That classical computer makes some approximation itself because you can't do this exactly. And they say, my answer is 0.32. This is my answer. And so now one has to argue between the two which one is correct. And that is an interesting point that one could make, that we're asking not just sort of, it's fun to poke holes at quantum computers, it turns out, but we're getting to the point where we're asking questions of, whose approximation is better. And I think in the case, I tend to believe the matrix product state version is a little bit better. You can control it. You can look at some extrapolations. And also it took 1 hour on a commodity device, not a day on a $1 billion device. So it's sort of, it's an argument to be made for the matrix product state. But yeah, we're getting to the point where we have to think very carefully about whether our classical algorithms are approximating very well and whether the quantum computer in its noisy state is doing something that is interesting or trivial. We still have time for a few more questions. All right.